Hello, we're the TI Elbow team. Today we'll be presenting the TI Orthotic Elbow, sponsored by Texas Instruments. The team is comprised of David, Joe, Nathan, and Raphael. Our project explores a powered programmable elbow orthosis, which stabilizes, limits, and assists the movements of a user's elbow. Specifically, this project restores upper arm functionality to users suffering from a range of injuries and disorders, namely ones which weaken muscles and muscular activity. The orthosis intercepts weakened muscle signals, discerns muscular intention, and subsequently drives a motor to help articulate elbow movement. A user interface allows for dynamic manipulation of desired settings, and a battery supplies portable and long-lasting system power.
The body-to-sensor interface uses a combination of angle, pressure, and electromyography sensors to encode the current and intended elbow movements. Various analog and digital filters help distinguish the relevant muscle signals from noise. Using a microcontroller, the data processing subsystem interprets the filtered signals, manipulates the information per user specifications, and translates the result into a pulse width modulated motor signal.
The motor-to-body interface takes this signal, actuates the motor, and articulates the elbow. Feedback sensors and a properly tuned transfer function ensure smooth motor movements. The power subsystem provides portable and sustained power to each component of the orthosis. The user interface subsystem allows for dynamic calibration, data display, and customization.
The body-to-sensor interface includes an analog-to-digital converter and a rotary encoder. TI's ADS-1299 converts an analog muscle signal into a 24-bit digital value. The rotary encoder registers angular position by tallying a number of ticks. The ADS reads muscular activity through 3 gel electrodes, a positive, negative, and bias electrode. In this demonstration, I will strain my muscles with varying intensity. A higher intensity signal indicates a greater desire to move the forearm. First, I collect a calibration signal by restraining my arm and flexing. All future signals represent a fraction of this maximum measurement. Next, I move my arm without resistance. Then, I move my arm with a little resistance. LabVIEW software then analyzes the muscle signal. In the unfiltered signal, electrode drift causes a smooth rolling signal. A digital high-pass filter then stabilizes this signal. Up close, the calibration signal, unweighted, and weighted signals are clearly distinguishable. Research indicates that these signals scale linearly with intended force output. Furthermore, the signal densities and magnitudes provide a direct link to user intention. Digital rotary encoders transmit angular position by pulsing a square wave along 2 channels. Whichever channel pulses first indicates direction. In the first example, the yellow pulse precedes the green pulse, indicating clockwise movement. In the second example, the green pulse precedes the yellow pulse, indicating counterclockwise movement.
I'll be demonstrating the data processing subsystem's SPI communications with the logic analyzer. The SPI transmission is used to communicate with the body sensor interface. The MSP432 is used for this subsystem because its low power capabilities. The SPI clock and transmission pins from the MSP432 are connected to the logic analyzer. In the final system design, it will be connected to the ADS-1299. The logic analyzer is continuously displaying a 500 kilohertz clock signal and transmission signal of 0x08 hexadecimal, which also coincides with the ADS-1299 start control signal.
The first prototype of the elbow orthosis consists of 2 hinges, with the torque being applied at the main center gear. We connect a small stepper motor using gears and supports. Once in place, we drive the motor using Code Composer and a GUI. From the very beginning, you can see that the motor is having difficulties moving the orthosis. By only applying torque at one hinge, we created a heavier load. A better option would be sharing the load using 2 motors. This also allows us to use smaller motors, which reduces the profile of the structure. Here we have a test box that mimics the torque that would be applied to the motor using the orthosis. A radio encoder has also been added to know the position and correct for error.
As you can see in the power flow diagram, our system currently uses a bench power supply. The supply's 12 volts are reduced to 5 volts through the use of a buck converter. The 5 volts are then run through the ADS-1299 power circuit. the circuit produces two analog voltage sources, one at positive 2.5 volts and one at negative 2.5 volts, and one digital source at 3.3 volts, as specified by the ADS datasheet. Our MSP432 will also draw power from this circuit as it produces the appropriate 3.3 volts. A bench supply is being used so that multiple types of motors can be tested without being constrained to a single battery type, with an actual rechargeable battery being decided once more components are finalized. The circuit is currently protected by two fuses rated at the device's specified current. The following voltage regulators were used to achieve the desired voltages. There is a second regulator for the 3.3 volts that reduces the noise that would be sent to the ADS 1299. Here you can see the 5 volts from the buck converter, 3.26 volts from the LM117, positive 2.8 volts from the LP59, 3.27 volts from the second LP59, negative 3.27 volts from the LM2663, and negative 2.5 volts from the TPS. The first LP59 gave 2.8 volts due to the IC ordered being rated for a 2.8 volt output. The appropriate regulator will be ordered later. Here you can see the circuit powering a microcontroller with some test code. For the user interface, we will be utilizing a TI Chronos. The watch will communicate with the MSP432 using an RF booster pack. The user will set the angles which the orthosis will not pass and will be able to calibrate the system's EMG sensors by flexing different muscles. To set the orthosis, the user will use the top left button to cycle through the menus until they hit the calibrate option. They will then hold the button to enable communication between the microcontroller and the watch. The user will then hit the top right button, then set their upper angle limit by moving the forearm as far up as possible. Then they will hit the bottom right button and move their arm in the opposite direction. The user will then hit the top left button, setting the system and returning the watch to the clock. In conclusion, the powered programmable elbow orthosis stabilizes, limits, and assists the movement of a user's elbow. Upon introducing the proper electrical muscle signal to the electrodes of the elbow orthosis, the orthosis subsequently filters, converts, communicates, and analyzes the collected data to discern intended movement. After processing intention, the orthosis pulses a signal to drive the motor. Throughout the process, rotary encoders and force-sensitive resistors ensure the stability and safety. Furthermore, a battery efficiently supplies portable and long-lasting system power. A user interface allows for dynamic display and manipulation of desired settings. Thank you for watching.